everybody, my name is Jeff O'Connell. I'm a professor of mathematics at Ohlone College in Fremont, California, and I'm also the guy who gave the TED Talk, Imaginary Numbers Are Not Imaginary. This was a TED event that was hosted at my college, and the theme for the evening was Defining the Undefined. When I was asked to participate, I was so excited, kind of terrified, but mostly excited, but mostly terrified. If you ever get the opportunity to give a TED Talk, you should totally do it. It's an exciting, terrifying event. You need exciting, terrifying events in your life. Like I said, the theme was defining the undefined. And as soon as I heard that theme, I knew I had my topic. In the math department, we absolutely took something that was undefined and we defined it. That's where imaginary numbers came from. And I had always kind of thought throughout the course of my career that imaginary numbers are kind of this odd thing that we teach algebra and pre-calculus students about imaginary numbers without ever really giving them the reason why imaginary numbers exist. And the answer to that question is that imaginary numbers come back to us when we are studying physics and differential equations, which is a long way from algebra and pre-calculus students. So my goal in that talk was to kind of try to demystify the idea that imaginary numbers were something that your math teacher, that your algebra teacher made up just to make your life miserable. This past semester, I was lucky enough to get a sabbatical, and one of my sabbatical projects was to make a bunch of videos that supported my TED Talk. You'll notice in the TED Talk that there's a lot of reference to math that is going on, but there isn't a lot of math. If you give a TED Talk and you put a bunch of math and equations in it, not many people are going to be interested in your TED Talk. Like I said, I was trying to bring people who were not interested in math into the conversation. The point of this video is to try to tie those other videos that I have made to support it together. And you will see all of the videos referenced in the comments below. The first video is a derivation of the pendulum equation. I use the pendulum in the TED Talk. This is a second order differential equation. I also have a derivation of the spring mass equation, where there is an explanation for how all of these things come about. Both of these derivations require a knowledge of first semester calculus, as well as in the case of the pendulum equation, first semester physics. We use the conservation of energy equations. Both of these differential equations are called second order homogeneous differential equations with constant coefficients. That's quite a name, isn't it? Let's pick this apart piece by piece. Second order means that in each one of these equations, the highest derivative is a second derivative. You see that both of them have got a double prime in there, so that's why it's called second order. Homogeneous has to do with the fact that we take the dependent variables and always put them on the left side of the equation. In the pendulum equation, the dependent variable is theta. In the spring mass equation, the dependent variable is x. And then if there's any term that involves the independent variable, in both of these equations, that is a t, then any term that involves only those goes on the right side of the equation. If the right side of the equation ends up being equal to 0, then we call that differential equation homogeneous. So this is a second order homogeneous differential equation. The constant coefficients part has to do with the fact that what each of the dependent variables is being multiplied is a constant. In other words, it's not a function of t. So both of these are second order homogeneous differential equations with constant coefficients. Now, if you take a differential equations class, you will find that the way we solve these differential equations is ultimately through roots of polynomials. So for example, let's say that we wanted to solve the differential equation 1x double prime plus 5x prime plus 6x is equal to 0. This is a second order homogeneous differential equation with constant coefficients. It can be shown that the roots of this, that the solutions to this are of the form e to the rt, where r is a root of the polynomial that has the same coefficients as the differential equation. In other words, we have taken the solutions to a differential equation and we're going to get to the solutions of the differential equation by looking at roots of polynomials. Roots of polynomials is something that you look at in an algebra class or in a pre-calculus class. In my example here, this polynomial factors and gives us roots of -2 and -3, and that means that our solution is a linear combination of e to the -2t and e to the -3t. The constants c1 and c2, we will find those based on the initial conditions of the spring mass system. That is, its initial position and its initial velocity. Next, let's look at a simplified version of the pendulum equation, theta double prime plus theta is equal to 0. If we look at the polynomial in this case, it's r squared plus 1 is equal to 0, which has roots that are imaginary, plus or minus I. So what we just did would imply that the solutions are e to the it and e to the -it. While imaginary numbers and complex numbers are great tools, they do not exist in the real world. I cannot talk about a distance of I or a length of time that is a complex number. We need to be able to take these imaginary numbers and put them back into the real world. And what allows us to do that is Euler's formula. Euler's formula is an absolutely amazing result that shows us the relationship between imaginary numbers and sines and cosines. There is a proof of Euler's formula below. That proof does require understanding some algebra 2, that is powers of imaginary numbers, but also understanding the concept of a power series, which is something that most people would cover in a second semester calculus class. But again, it's an amazing result that allows us to combine, or allows us to relate imaginary numbers and sines and cosines. Through a little bit of math that you would cover in a differential equations class, we can show that the solution to this differential equation is a linear combination of cosine and sine. I have left out some details here, and if you are interested in those details, I look forward to seeing you in my differential equations class. I talked a lot in my TED Talk about dampening, and let's look at an example of that in a little bit more detail. Let's say that I have a spring mass system x double prime plus 2x prime plus 5x is equal to 0. Here, the polynomial is r squared plus 2r plus 5 is equal to 0. And that gives us roots that are complex numbers, a combination of a real number and an imaginary number, -1 plus or minus 2i. So that would imply that one of the solutions would be e to the -1 plus 2it. I could rewrite that as e to the -t e to the 2it. And then, again, leaving out some of the details and using Euler's formula, I'm able to get that it is a linear combination of e to the t cosine of 2t and e to the t sine of 2t. Now, I understand that's a bit complicated, but when you look at how graphs of these kinds of equations look, what you end up seeing are oscillations, but the e to the -t factor dampens those oscillations. So in effect, it is reducing the amplitude of the sine and cosine in the solution. So I hope that this video and the other videos that are attached to this kind of tie together some of the math that was behind what ended up happening in that TED Talk. Thank you so much for going on this journey with me. It was a great journey for me to go on. I'm immensely proud of the work that was produced by that TED Talk, and just a little life lesson about how when you put yourself out there, good stuff comes. I am so excited about the feedback that I have gotten from my TED Talk. I actually had a producer at the BBC reach out to me after watching the TED Talk, and I was invited to participate in a podcast called The Curious Cases of Rutherford and Fry. Rutherford and Fry, of course, is Hannah Fry, the massively huge YouTube star mathematician. and I was able to participate in a episode they did about imaginary numbers. What an amazing experience that was. Also a little terrifying, got to admit. And to just hear Hannah Fry say your name and where you work is also a really, really cool event. As always, feel free to reach out, make comments below, tell me what you liked, tell me what you didn't like. I always appreciate the feedback, and I look forward to seeing you in the next video.